So in the last video we did acid catalyzed hydration, and we made a carbocation intermediate. When we did that, carbocation intermediates are subject to rearrangement, and this next method is a way to produce a Markovnikov addition of water without carbocation rearrangement. So if we start with our double bond, here, what will happen is we will have an oxymercuration. And this will be the result. We'll put the hydroxy here at the more substituted position. Here's the more substituted position of our original molecule, and that's where we've got our hydroxy. And we have this mercury compound stuck out here where we normally have a proton. And then we'll do a demercuration. And we end up with our result. Now, the reagent in this reaction is a mercuric acetate, and it is in equilibrium with a mercuric cation. See that positive charge there? This is a powerful electrophile. It will be very attractive, or is very attractive. These pi bonds just love to come over and attack that positive charge. So let's see what happens. First, let's do an example of an acid-based hydration, and why we're doing all this to avoid. So if we've got this compound here, and we do an acid catalyzed hydration, we have let's go back to the blue. We've got an acid here, and we're going to, these pi electrons attack that proton. These electrons go back, and that makes just plain old-fashioned water. I think I put 4 hydrogens around that. That's kind of interesting. All right. You don't want 4 hydrogens around an oxygen. Here we go. Our hydrogen that we added goes at the less substituted position, because this is going to be Markovnikov's, right? And we produced a carbocation at the more substituted position. This is a secondary. This will rearrange. We can get a, let's do orange. There can be a hydrogen here, and it's going to migrate down to that carbocation. And getting too many different colors here, but we've got, I thought I changed to blue. We'll get a carbocation that's tertiary and more stable. And then our water, when it comes in to reacts here at this position instead of maybe the position we'd expected it to interact. And the end result will be, got a couple, we were doing the reaction mechanism, which is a couple things. We'd end up with a hydroxy at, let's see, at this position instead of this position like we'd expect. So the whole goal here is to avoid this rearrangement. Let's see how we do that. Here's our substrate, and here's our mercuric cation. It's positively charged, and the pi electrons that are attached in this bond are going to be very attracted to it, and then it's going to produce, go back to the pink, bond that's going to be in equilibrium with carbocation. The mercury is here. That's also going to be like this. So the mercury is attached a little bit to both carbons. That is enough to keep the whole thing from rearranging. This position, let me get a different color, this position right here is still subject to nucleophilic attack. A nucleophile will like to come in and attack that. But it's stabilized so that it does not rearrange while it's waiting to be attacked. The carbocation is stabilized. Okay, so the pi electrons attack the mercuric cation, but the mercurium ion is formed, not a carbocation. The carbon is positive enough to be attacked, but we're not going to go rearrange. I just said that. All right. Then the mercury needs to be removed by demercuration, and this is done with treatment with sodium borohydride. So let's look at these and see if we can predict the products. This would be a good place for you to stop the tape and see if you can figure it out. Okay, as we said, these are going to be Markovnikov additions, so we expect the hydroxy to go at the more substituted position. This is the more substituted position, so we'll expect to get a hydroxy right there. Now, if we had not used the mercuration demercuration method and used acid, we would have gotten an intermediate that looked like this. This is a secondary carbocation, and it would have rearranged. We would have gotten that methyl group would have moved over, and we would have gotten this, and finally the hydroxy would have ended up at this position if we had done acid catalyzed. So if we want the hydroxy where we want the hydroxy, then we have to use the mercuration demercuration method. Okay, so let's go on. For this one, we want to put the hydroxy at the more substituted position, so that will put it right here. For this one, we did not add, we didn't add water. We've got ethanol. Ethanol can also be a nucleophile. It's got an oxygen with a lone pair on it, and so it will appear right here. It can attack just in the same way that the water attacked. And here we would get an amine, because we have an amine group. Actually, it would have just one hydrogen and ethanol on the other side.